Okay, thanks for the introduction. And then this is first time for me to participate in global webinar on material science and engineering. So since I am covering this topic for the first time, I will cover some basic background, but there are so many capabilities of the AFM and SPM. So I will try to introduce many of the capabilities, then to focus a few capabilities in depth. And actually, my intent was to cover like some interesting historical fact that people doesn't know. But I changed my mind. I will put put more scientific kind of a data. And then I really enjoyed Dr. Rothman's presentation because. So while listening to his talk, I also put some of the kind of graphene Moir patterns detected by AFM. Well, anyway, I hope I could deliver the message that this diverse SPM technology is not competing, but complementary technology to most of the important measurement technology to advance material science engineering field. Okay. Okay, so AFM is not like a typical optical microscopy, but you all know about it, but it's rather the probing robot. And then there are not just kind of providing high resolution, but there's so much more benefit you can get from AFM. And then this is the kind of a first generation electron microscope. You all know it, but Professor Ruska, who invented the electron microscope in 1931, and they received the Nobel Prize in 1986. It means he waited 53 years, but Gottbeinig and Heinrich Rohrer, who invented the first scanning for microscopy, the scanning tunneling microscope, received the Nobel Prize just after 6 years. Okay. And this is the first AFM paper, which is published in 1986. And then, so when you see it, there's a Gottbeinig, who also involved in inventing first STM. But the co-author was the Carl Quate, the professor in Stanford University. So this is the first AFM used in the first paper. And then this 3 authors received the Cavalli Award 30 years after the first publication. At that time, this Dr. Sang-Il Park was a graduate student working in the Professor Quate lab. And so, as a reminder of a quick history, many people know the FTM. The first FPM was invented in IBM Zurich, but not many people know the AFM was really actually invented in the 1985 at Professor the Carl Quate laboratory at Stanford University. But anyway, so Dr. Sang-Il Park, he after graduation, after he received the PhD, actually he founded a Park Scientific Instrument in Silicon Valley to commercialize AFM for the first time. So probably we can say Park System has the longest history in manufacturing in AFM. And after then, finally, since the 2022, we become the market share #1 in whole AFM market. So because we only concentrate in focus on our research and development in AFM area. And the growth engine for this change was due to the kind of a successful entering of industry, especially semiconductor market. So it takes about 50 years for electron microscope to become industrial analysis tool, but AFM becomes an industrial tool in 30 years. And anyway, so in order to become inline wafer fab inspection tool, AFM has to incorporate various automation, has to be kind of implemented. And the future of semiconductor technology is driven by the new application-driven devices and systems, such as big data analytics, physical systems, simulation, and artificial intelligence. In order to achieve such functions, kind of complex 3D structures need to be fabricated using new materials and processes with ever-decreasing dimensions. Now you can see all kinds of devices with weird-looking structures, tiny and high aspect ratio structures, like in the coming years. This development is also closely related with material research, including graphene research, just Dr. Rossman introduced. So in result, AFM is becoming more valuable than ever with the decreasing dimension and in advanced material research too. So to provide a quantitative measurement data, so because AFM was kind of considered as qualitative the measurement tool, because when you measure there's so many errors could be implemented, but then we cannot use this technology in the industry because they already. So most important thing is accuracy, and then repeatability and reproducibility in industrial application. So we redesigned the AFM scanner. So we separated XY scanner and G scanner, and then this XY scanner make a very flat scan. So when we imaged the optical flat, and this background coverage was less than 1 nanometer across 80 microscan. And this closed loop XY scanner also has excellent linearity and orthogonality. And the flat XY scanner provide distortion-free images and then pretty good orthogonality. This is actually very important thing, because recently we found out, actually like 2 months ago, for when we imaged the high resolution in a nanometer level, so we found out our measurement actually really can correlate with the theoretical model. So exactly, so so this proves that this design works in that part. And then also once we separate the G scanner, it will it can have the higher bandwidth because they are light mass under the G scanner. And then we use this the eigenfrequency of the cantilever to use the making non-contact mode. But I'm not going details in how we do it because it takes too much time. But I just want to emphasize that this is not easy to do the non-contact mode. So when I presented the non-contact mode like 15 or 20 years ago, people said that I'm lying because they have been working in this AFM field for 20 years, but they try to do it, but it's almost it's very difficult to make it realize. So the reason is that when you see this non-contact, so it's they have when it approaches to the surface, it's not monotonic. So the response. So as the tip gets too close to the sample, the tip enters into the repulsive force region, and the tapping mode starts to occur. So due to this binding force, the amplitude is just suddenly increase, and then so when tip is withdrawn beyond the mode hopping mode, this system remain like in the tapping mode for a while. So in order to do the non-contact mode, they have to be maintained in this bistable region, and then and it is not easy to do it actually. So because in order to achieve the stable non-contact mode, the tip sample interaction force must be accurately measured and controlled to remain within this non-contact area, which is plus minus 1 nanometer in amplitude, and then plus minus about 2 nanometer in G distance. And this is a really a difficult thing to do in mechatronics. So in order to achieve these things, you have to have a very low noise in the system, and then you have to have a fast G server system. That's why we separated XY to G scan. And this is one of the example how non-contact is shows. So even after just 100, actually the 10,000 scans, and tip stays the sharp, That means that you can have same data and after image by after the image. So that way, so industry, they can believe their data of the AFM data. And then also when you compare the scanning electron microscope are the kind of a thing for the detecting or analysis of defects. But before, when we try to see large structures, SAM was considered as a non-destructive measurement technique. But when you focus these ion beams, actually it makes damages on the surface. Actually, it can make damages like this. And then also some aerial type defect the SAM cannot detect, but the AFM is so sensitive, they can detect even these aerial type defects. So this is a kind of a photoresist, and then in order to inspect if photoresist is well formed, but with the electron microscope, they make damages. So it's a first rectangle outside, it's making about 10 nanometer dishings. And even inside, again, they make about 5 angstrom additional dishings to the 10 nanometer dishings. But AFM can even detect those kind of fine changes without damaging the patterns. So FPM technology has a kind of greatly influenced the nanotechnology and research on new materials. And until now, research on developing FPM technology itself has been more active than researches utilizing FPM technologies. So I think, but in near future, I think we expect more effort to utilize SPM technology, including its use in industry and material science. So this is kind of example. So the best part of the FPM technology is its high resolution imaging capability. So in a variety of environments, right? Not just in air, but it can operate in vacuum and liquid. And so since there's a few environmental constraints, it is great advantage for researchers to be able to observe dynamic changes in sample surface. This is a melamine and thioric acid formed on HOPG, and then this lattice period shows like less than 1 nanometer. And then it's about, so when I showed in early about AFM paper, so this actually capabilities kind of 3 times better than it was described in the first AFM papers. And however, AFM has much better vertical resolution than lateral resolution. So if you look at this gallium nitride and the silicon epi film, it clearly resolved 2.8 the angstrom atomic steps quite easily. And then AFM could also resolve the kind of biological samples, because many people try to manipulate DNA in not just the biologists, also the nanotechnology, the researchers. So this is a DNA origami in liquid conditions. And this liquid phase high resolution imaging capabilities is telling us the possibility of kind of driving a variety of innovations in molecular biology research too. And one of the technological advances in kind of mechanical characterizing mode is a pinpoint mode. Kind of a topography, stiffness, and adhesion force maps are acquired simultaneously in real time from high-speed force distance curves at each pixel. And we could optimize the data collection by controlling the contact force, dwell time, approach retract speed, and retract distance. So since we can manipulate all these parameters, so this is one of the really the popular mode for the kind of basic material science kind of researchers. And this is one of the examples. So this is the kind of quantitative data on so you can get quantitative data on modulus and stiffness, and so bringing new wins in the field of characterization of viscoelastic materials, particularly kind of the polymers. And this is the kind of information you can get from this pinpoint mode. and you can get kind of a modulus and deformation, adhesion force, and adhesion energy, energy dissipation, and stiffness approach and stiffness retract. So all these kind of mechanical properties you can get from the pinpoint mode the applications. And not just the mechanical mode, pinpoint actually can even get other properties, and then additional benefit is pinpoint mode optimized kind of or minimizing measurement artifact, as well as kind of in the kind of other method like contact or the tapping mode, because it removes the lateral motions of the tip movement. And this is a cross-section of a lithium-ion battery electrode, which was characterized with the pinpoint mode in vacuum. And then this is one of the example. So actually, this is in the LBN, the Lawrence Berkeley National Lab, when they researched this perovskite, which is famous for solar cell materials. So at the time, they have all kind of AFM, but they couldn't make this measurement. So they contacted us to be able to measure this electrical efficiencies of the perovskite material without destroying the material, because it's a very brittle materials. So we kind of help them to measure local short circuit current and the open circuit voltage measurement, and then with the calculation we could calculate we can provide the energy efficient map of the perovskite. So at that time it becomes a very big news in kind of in many medias, because it shows the possibility of improving the kind of efficiency level of the perovskite materials. And not just the kind of the electrical measurement, also the AFM can magnetize the cantilever, can detect the magnetic properties. So there's several ways to do it. But at this time I'm not going details in this area. And FPM technology could provide a various property characterization in electrical mode, like a potential, in SKPM, current in EFM, and capacitance in SCM, and then also FMM in the mechanical property, and LFM for the tribology, lateral force, and the scanning thermal microscopy to detect the thermal properties. So multifaceted nanocharacterization will be an essential element in the study of new materials, and AFM could be the big part of those applications. And this is a kind of a new slide I just put while listening to Dr. Rossman's the presentation. This is graphene and HBN, and then so you can see, you can zoom in and you can see the structures. And this is the multi-layer graphenes. See height and also potentials, you can image it. So this is a 10 micrometer scan, but recently we also are measuring this graphene to see the Moyer patterns. And then this is about the 50 nanometer by 50 nanometer scan, and the 15 nanometer by 15 nanometer scan. You can see this, how this Moyer patterns and shapes, and different angles shows kind of a different patterns. Like this. And then and there are many hybrid technology to combine AFM with other technologies. So AFM is a kind of providing unique data. So it's really the complementary technology. So among them, I will just quickly introduce nano IR technique, because I think this technology will make a huge impact on many science and engineering, including material science. So now we come to the very kind of a significant application, a chemical analysis on nanometer scale. So actually people call AFM blind microscope, because what we can detect is a topography, and then the color map is not real color. Actually, color map shows the height or current or other properties. So it's very hard to detect chemical properties using AFM. So when I see this nano IR technology, I was so amazed that with this, we have new possibilities with this scanning probe microscopy. So this technique utilized the metal-coated AFM tip with a tunable infrared laser. The metal-coated tip acts as a nano antenna and produce a tip-enhanced field at the apex of the tip. So when the sample observes the tip-enhanced IR field, an attractive force whose magnitude is proportional to the absorption strength gets created between the tip and the sample. So by measuring the power of this attractive force induced force as a function of a wave number, and we can acquire the photo-induced force IR spectrum, actually which really correlate well with the FTIR data. So the important thing is that most line spectroscopy uses a photo detector as a sensor, so which significantly limits the lateral resolution. The most significant difference is that the PIFM uses a tip as a sensor to enable us to analyze it in a kind of an excellent resolution, even less than 5 nanometer. So this is comparing analytic technology. So you can see the signal is much higher comparing to FTIR and Raman. And because of the tip is detector, we can easily go to the 10 to 20 nanometer resolution and even lesser. But with the FTIR, kind of because of the beam spot size, about 10 micrometer is the kind of become limit. But spectrum range are a little bit limited compared to the other technology, but depends on what you require. So laser can be changed to expand these spectrums. And then, so this is the kind of another explanation. So in FTIR, so IR light go through the sample, and then this IR absorption takes place, and then others are detected by detector. So, but the PIFM measures the sample response to IR light using AFM tip. So, kind of this is a little bit more detailed. So, it's actually we are detecting. People call it detecting a dipole movement, but I want to emphasize that this photo-induced force kind of interact only directly below the tip. So the spatial resolution is at the kind of at the AFM resolution level we can acquire. So this is one of the data. This is the PMMA black hole polymer. So it's in wave number 1493 to 1733 is a different material, and then we can combine it to see the distribution of this PMMA and then PS materials in nanometer level. And then when you look at PIFM for these PMMA materials, we can see how well they kind of align with the FTIR data. And this is a PIFM. So when there's kind of a wafer defect, there's a so when you see the topography, it looks like one materials. So, but with the different the wavelengths, we can see that this material, this defect is composed of two materials, not one materials. So this way, this PIFM also can be used in industrial the industrial field. And then recently we also introduced a new class of atomic force microscope called the FX40. Actually, it's already 2 years. And then actually for AFM has many capabilities, and it's a very useful machine, but it's kind of hard to use because in conventional AFM, like in order to get one images, you have to go through like how many steps? 18 steps to get the one images. And if there's something wrong, you have to go back to number kind of 5 to do it again. But with the FX40, since we are kind of pioneers in the automation in industry, actually we apply those technology into the research grade machine. So you click just 3 clicks, and then you can get the kind of AFM data. So there's many automation features, but I will just explain. I will just introduce a few of the kind of features. So in cantilever, we recognize a QR code on the cantilever, and then so it will kind of record the probe type and model and available AFM model, and then when you use it, and we will see that how long you haven't used, and then if you have to change a new probe or not, those kind of all information can be stored. And then this is a auto probe exchange. So like this a machine learning algorithm of a vision recognition detector ensure the probe is loaded correctly onto the designated probe slot, and then smart vision recognition locate the position of the loaded probe. So it generates the status report during the probe loading. So the magnetic force kind of a control mechanism pick up and then design the probe in the A probe cassette. And it provides the automatic probe positioning by using mechanical it's machine learning also. So it automatically position and align the laser beam onto the proper location of the cantilever. And it automatically fix the laser beam to the center of the optical microscope vision, and it allow you to kind of laser align by moving optic stage to cantilever positions. So actually, so when photography technique was first introduced, I'm using it as an analogy. So early photography was literally a technique that only a few experts with the skill could use. Then in 1888, Kodak ran this advertisement. It's like kind of you just press the button, we do the rest. So as a result, photography became popular, and Kodak led the camera market for the next 100 years. So I hope this kind of ease of use is also can have a kind of a potential that people can get the benefit out of the atomic force microscope. So there are so many things to say in AFM, and then there's many development is coming. So because of the time, I cannot introduce everything, but I hope in specifically material science and engineering, the AFM become invaluable. And then I hope, so if you have any questions or if you have difficulties in applying those techniques into your research, please let me know so we could assist those kind of research. Okay, thank you very much.